Hi people, it's Friday, so homework out. No, not quite. I love to say homework collection, but it needs to be on OneNote for a few weeks. So if we can pop that homework onto OneNote, we should be doing it today or maybe before today. That would be good, wouldn't it? All organised. Right. There are 5 questions here. It says have a go at them on the big whiteboards. So, new topic we're doing. But you'll remember the hyperbolics from last year. Carrie Ann taught them well. So can you have a go at those 5 questions? Now I'll shut up. If someone could pause me while you have a go on the big whiteboards if you want, but if you're scared of those, you can do it on little ones. All right then, have a go. Okay, so we've unpaused the video now, so the answers will appear. That's the first one, second one, third, and fourth, fifth. Okay. But we agree with those answers. And now let's have a look then. So hyperbolic sheets. I think you've got this one. We gave them out. But as I say, if you've not got it, there might be a few spare, not many, in the green tray on the white shelves. The green tray on the white shelves. Don't rustle too hard in them. Things have been put in order. There might be the odd hyperbolics lesson 1 sheet free, and if there isn't, then sorry, you were given one previous and you'll have to make your own notes for today, or you can print them off later. Right, what have we got? Hyperbolics. We've got a recap work from AS, hyperbolic functions and their inverses. We've got to define the reciprocal hyperbolic functions sec, cosec and coth, like you've seen reciprocals in year 13 on the other ones. That's what we've read. You've read cosh and, oh, we've met cosh and shine, haven't we? We've met them in, not in, yeah, we found them in further maths AS, didn't we? We're going to draw the graphs of the reciprocal hyperbolic functions. We're going to know their range and domains, look at them on graphs, and we're going to write the inverse reciprocal hyperbolic function in logarithm form. Wow, that's a lot to take in. So we'll start off. Recall hyperbolic functions. These should be good friends. Shine and cosh. Shine is a half e to the x minus x to the minus e to the minus x, and the only difference is that cosh has a plus in the middle. The graphs of those two, you can plot them on your calculator, but here they are. There's shine and there's cosh. We must write down the range and domains. You've been doing those in normal maths, range and domains. So, what are they? I'm sure you put them in already, but if you haven't, right. So the range and domain here, the range, remember that's like the y values, so that could be anything, couldn't it? So we'll write that as f of x, because this is the f of x, like f of x. So f of x, because it's a function, we're going to say that belongs to the real numbers. Anything then. The domain, well, the domain, if you carried it on forever, yeah, it would go, x would expand, maybe not as quite quick as the y, but it would expand. So x can also belong to the real numbers. The cosh graph, though, a bit different, isn't it? The range, can you guess that one? What's that going through? Oh, You might have done it. It's 1 to infinity. You can go from 1 to infinity. How can we write that for range? We'd probably write f of x can be anything bigger than 1. And the domain, that's the x value, is going to be anything. Probably would go on forever. So yes, the x belongs to all the real numbers, could be anything. Belongs to, that's simple if you didn't know. Should know by now though. Right, next one. Oops, wait a minute. Gosh is an even function because you see it's symmetrical around the y. And shine is an odd function. Tanh, or tanh is that because it's sine over cos. So it's been rearranged. You've done all that from rearranging that one over, dividing this formula by that formula. You will in fact get that eventually. You'll have done that in last year. But the graph of this one looks like this. And so for it's a range and domain for that one are, as it says over here, x, as x tends to infinity, y tends to 1. As x tends to minus infinity, y tends to minus 1. When x is 0, tanh is 0. So I haven't written range and domain there, have I? So let me squeeze them on. So the range is f of x can be between -1 and 1. Oh, I shouldn't have equal to, should I? It doesn't equal. Terrible, terrible. They can get it to equal. No, there are some tools. Is it? No, these. No, it doesn't touch. And the domain is x can belong to anything. Right. That's those. Let's go to the next slide. We call inverse hyperbolic functions. You might want your graph mode for this, option F3. So have a look. Let's have a look. Oops. Graph mode, option F3. Hyperbolics are there on the screen if you look. Anyway, use your calculator to sketch the graph of shine to the -1. So if you try or go at that, so y equals, follow that options, graph mode option F3, and then shine to the -1 of x. Now look, does it look like the three pictures we're getting? You could draw them. Could exit and try another one. So it's option F, you have to press option F3 again, don't you? X. Hopefully they give you them. Yeah. Right, so it's those three that they're probably a better picture than what you'll get in your graph. God. Right, so what can we say about these? Let's do some range and domains for these. No, right, so shine first. What's the domain on shine? Well, shine would go on forever. Domain, that's the x value, so that could be x belongs to the reals. It looks like y belongs to the reals as well, but we haven't got that to write on here. I've got no room. This next one, what about the domains of this? The domains. Range on, couldn't we? F of x also belongs to the reals. Right, cosh, the domain, it's starting at, because it's been, yeah, it's starting at 1, so anything bigger than or equal to 1. And the y values then, so f of x is greater than or equal to 0. And tanh, At the moment my face is covering up that thing, I'll move it later. But you want the domain here. It's going to be our domain. X is between, oops, what am I doing a bracket for? You're probably telling me, shout at me, X is between what and what? Yeah, between -1 and 1, and f of x. Well, that could be any old number, couldn't it? And you should see a relationship with the other graphs. If you remember when we do the inverse, then the domain and the range switch over. So look, the domain and the range are switched over there, and they're switched over there and there. Spot on. Right. We could have written that last one as mod x is less than 1, so between 1 and -1. Okay, so it says in A-level maths course you looked at transformations on general functions. Yeah, we should have done. So all these things should not be a surprise. So if we use y equals, let's use y equals shine x, and see what would happen. So a translation of A units in the y direction. So if you use replacement method, which I advise you all do, and if you're doing that, you would replace the y with y take A equals shine x, and you get y equals shine x plus A. Next one. Change pen, then you can see where we're going. If you've got a translation of A unit minus A units in the x direction, right, minus AX minus this in the x direction, so basically it's asking for the translation of minus A0. Well, that would mean you replace the x with x take A, so double take means plus A, doesn't it? Plus A, and that's what we get for that one. That will move the graph back. If we've got a reflection in the x-axis, if you reflect something in the x-axis, it's the y-coordinate that changes. It goes from +2 to -2, so or whatever it is. And this one is just -1. So it just changes from plus to minus. So it's the y value that's changing. So we replace the y with y over -1 equals shine x. Then you end up with y equals minus shine. Oops. I'm spelling it wrong now. I'm spelling the right silly thing, aren't I? Oh dear. Rubber again. Oh, different colour pen now. Don't make a mess now. Shine x. If we were to reflect in the y-axis, it is the x coordinates that change, isn't it? So we replace x with x over -1. So you've got, how many pens left? One. We'll have y equals shine x over -1, which just ends up as y equals shine of minus x, like that. Next one. We have got a stretch by scale factor A in the y direction. So if we've got a stretch by scale factor y in the A in the y direction, we replace the y with y over A. So I don't know whether this, let me just, oh, I've got a bit of space. Y over A equals sin x. So therefore we end up with y equals A sin x. The last one, if we want to stretch by scale factor 1 over A in the x direction, we replace x with x over 1 over A. So we'd have y equals sin of x over 1 over A, whatever the scale factor is, divided by, and then that is the same as y equals sin ax times top and bottom by A. Okay, well that's fun. Remembrance of normal maths. Let's try and apply it to something with the hyperbolics. Right, so transforming these functions. Sketch the graph of sin x and then do the transformation sin 2x to sin x and sin x plus 1. Oh, and a minus sin x. Rightio. I've lost the pen. That's here. So on each of these has been sin x drawn, and we're going to just transform them. So the first one, A. Let's have a look. What they've done there, they've replaced, if you can think of it, as they've replaced x with something, haven't they? So what they've replaced x with, they've divided by the scale factor, remember. So that must actually be sin x. If we divide by scale factor, x over a half to have been that. And therefore that's a stretch in x direction, I can't fit direction, by 1/2. So any x coordinate we're going to now half it. So when this was, that's 2, now it's going to be that at 1. So basically if you think of that as, let's pretend that's not going to be quite right, but pretend that was like 2 and 1.8, it isn't, but if we just like, now it would become 1. Oops, it would become 1 and 1.8. Yeah. So I'm not very good at these. 1 there. You could do it 0 to 0, stays 0 0, doesn't it? So it'd be like a version like that. It's concertinaed in. Right, next one. We'll change colour pen and then you not on red, blue. Right, so next one is 2 sin x. So if we'd had y, let's put y over 2 equals sin x. So this has been a stretch by scale factor 2 in y. So any point now, I keep picking this one here, which is really not true, but anyway, that's 2, 1.8 pretending. Then that would now become, stretching y by 2, it would be still become 2, but it would be, can't double that, 3.6. So that goes to 2, 3.6, so 2, 3.6, it'd be right up there. So it is again a stretch. This is the same sort of curve. Yeah, I really like that. It's similar to the last one, really. Right, C. What's this? So what have they done? We've replaced x with x plus 1. So it's going to be a translation So it's a translation, so it's been the translating the vector because it's in the x, and it's always replaced x minus, so it must be -1. So it's -1, 0. So it's a translation -1, 0. So 0, 0 becomes -1, 0. That 1.8 now will become 1.8. That wasn't quite right, was it? That's never 2. Oh yes, yeah, I see what I mean. The 2 should be 1.8. But the curve should be just the same as the other ones. It should be like run parallel to it. So it's not got steeper, just stays parallel to the curve. Very bad drawings. And the last one is D, not E. And we'll do that one. What have we not had? Get purple. Right, so this one, width's a reflection one, isn't it? And they've replaced, if you like, y over -1 equals shine x to get that. So it's been a stretch in scale factor -1 in the y direction. So it's going to be the y coordinates that change. So if that again was 2 along, 1.8 up, it would now be, because the y coordinates has got to change, so it would now be 2 along, but the y coordinates, what are you doing? I'm there, idiot. The y coordinates change, so it would be 2 along, it's here. Be Lucas putting me off. 2 along -1.8. There we go. So the drawing, oh, I'm not very good at these drawings. So that's going to become like that. And that one becomes like that. What about that rubbish? There you go. Hold on. That should be a bit of A-level maths, is that, isn't it? In BAS level. Actually, just right there, that was a reflection. It's the y coordinate changes. Right. Okie doke. Oh, those are the real answers. If they've been done on the autograph or somewhere. Right. Oh, this is a good one. So I'm going to give you a few minutes to have a go at this on your sheet. I think it's on the handout. See if you can fill it in. So we're asking you, what happens to cosh x? So I'll start you off as it comes around the arrow. Cosh x reflected in the y-axis. So remember, if reflecting in the y-axis, it's the x that changes, isn't it? So on that one, we'd have y equals cosh. You could write x over -1, but it's just basically a minus x, isn't it? Right, you carry on from that. So you work on this one. Oh, I should have written it in that box. What a brat. You work on this one now, you translate that one, 2, 3. Okay, you have a go. See if you can get round, and let's hope in a few minutes we'll all have the same centre result. So they're saying you're not going back to the cosh, you carry on with this one. So you're translating that 1, 2, 3. You'll get something, and then whatever that is, you're going to stretch that by scale factor 3, and so on. So 2 minutes. If you want to pause the board, that'd be great. Or pause the video, have a go, and then we'll start again in a second. Okay, on pause time. Normally I have someone up to have a go at this. A bit of a shame, and I can't ask you what you've got. So we'll have to trust my thoughts on this. So what would be next if I translate that 2, 3? So it's 2 in the x, and 3 in the y. So it becomes, I'll go right here first, y take 3 equals cosh. Now we replace x. Now it's minus, so it's brackets x take 2. Right. So that would be, if you wanted it as sorted out, we'd have that as y equals cosh of bracket, maybe it's minus minus 2, so it's 2 take x and plus 3. Right, then we've got to stretch in the direction of y by scale factor 3. So replace y with y over 3. So basically times up by 3, don't you? So we'd have y equals 3 cosh 2 take x plus 9. Then we've got to reflect in the x-axis, so that's the y that changes when we reflect in the x. So you replace y with minus y, and if I do that, I just take the minus over, wouldn't I? So I'll write y equals minus all of this, so it'd be minus 3 cosh 2 take x minus the 9, there we are. So now stretch in the x direction by a scale factor 2. So replace the x with x over 2. So final answer should be, or an equivalent to, that's what you should have. It's what I had when I did it last time. Super, I think so. Right. What have we got now? We have got order of transformations. Now you'll have met these in normal maths as well. So if two transformations are applied, the order does not matter if they affect both the x and y coordinates once. Right, that's a bit confusing. But we will, yeah, sort of makes sense, doesn't it? So e.g., this one, order doesn't matter. If we've got the stretch in y, we've got to translate in x. You can see that hopefully from that. It doesn't really matter about the order then. So I'll show you that by doing it both ways round. So if we translate by, start with this y equals shine x. If we translated by minus 3, 0, that would have given me y equals shine x plus 3. And then I've gone on to do a stretch by 2 in the y-axis, and then that would have given me, if you replace y with y over 2 equals shine x plus 3. So that leads us to y equals 2 shine x plus 3. That's the answer. If you'd gone the other way, it didn't matter. So if you started off with the stretch by 2 in scale factor 2 in the y, it would give us, would have started off with y over 2, so 2 whipped up, and you get 2 shine x. And then you've gone on and translated minus 3, 0. You replace the x with x take 3. There is no difference which way around you go. However, If both the transformations are affecting the x coordinate, or they're both affecting the y coordinate, then the order is important. We have to be a bit careful. Sometimes you go the right way round it, you don't have to be too careful, but if you go a different way around, you have to be careful. So if we look at this one, e.g. shine 2x plus 3, that t weren't very nice. Not before I spill it. Those both affect the x, isn't there? There's a stretch and there's a translate. So we can answer them in both ways, but care must be taken. So here we go. So starting with shine x, state the two transformations which map to that. So if we've gone for the translate first, well, we can see the translate's going to be, again, -3. And that would give us y equals, if we're starting with this original one here, shine x plus 3. And then we've gone on to stretch by 2 in the scale fact in the x direction, replace x with 2x. Oh, sorry, not stretch by 2, is it? Who said that? Putting me off. Stretch by a half in the x direction. This would give us x over a half, when we put over whatever the stretch is, plus 3. And that, when you whip the half up, it gives you the y equals shine 2x plus 3. So no worries there. We didn't have to be too careful. But if we went the other way around, you'd have to be really careful. If we'd gone for the stretch by a half in the x first, we'd have got, well, let's change my colour pen, I've got some room. Oh, wait a minute. Sorry about that. That was neighbour wanting an envelope. She's elderly. Right, sorry, so stretch in the half by the x, and I was changing pen colour, wasn't I? That would do y equals shine. Now we're starting back at the beginning with this thing, so it'd be x over a half, which leads us to y equals shine 2x. Now translate. I'll do the error, don't write this, and then you'll see why the error. I'll do the error in black because it's naughty. Naughty. Right, so if I'd gone for like, oh, let's think, I'm going to translate by 3 in the x. If I'd gone -3, thinking that will do, naught, and that would give me, replace the x with x plus 3. And then you'd open up where the y equals shine 2x plus, oops, 6. And we don't want that. That's not what we wanted. We want 2x plus 3. So I'll have to rub that out and we'll have to rethink that one. What we need to translate by is not the -3, but in fact we need to think of doing it by half of that, because we're going to double it later. So -1.5, or 3 over 2. And if we do that, that would give us y equals shine 2 lots of x plus 1.5, which then gives us y equals shine 2x plus 3, which is what we were after. So sometimes if you get the order, if it's, well, they say if it's in the x, if it's a change in the x, they're both in the x, translate first, and if they're both in the y, you'd stretch first, but you may not remember that, so just be careful. On the whiteboard then, try both ways of doing this, of changing shine x to y equals 2 shine plus 2. They are both affecting the y values, Always replace the whole thing. Anyway, so have a go, and then put your whiteboards up when you're ready, and then the teacher will know it's time to show the answer. If you want to pause me, that would be brilliant. Okay, unpause. Here come the answers. Hope you got them right. So on the first one, if you translated first, you had to be really careful. If you'd stretch first, then it wouldn't be, you'd not be too careful. Right, having done that, we have now got range and domains of transformed items. So given that f of x is 3 tanh plus 2 for x is real, here we've got a stretch in the y and an add. We're translating y, so we have to be careful. So which one's best to do? It's best to stretch first, really, when you've got a y one. So given that belongs to the a, x belongs to the real, sketch the graph of y equals f of x. So if I bring you back that graph here, if you can't see it, should say y equals tan x. That's the one we're going to be starting with in our brains. So if we do the stretch first, we're doing stretch by scale factor 3. We get f of x, well, we get, well, let's not do f of x, let's do y. Y would equal, stretching, oops, so you put it over 3 there, and then the 3 pops up, 3 tan that. What that would look like is it would go between, not minus 1 and 1, if it's been stretched by 3, it'd be going between minus 3 and 3. And then we've got another y thing, haven't we? So then we're on add 2. So that's basically translate not 2, because what you would do is you replace the y with y, take 2, and then we take the 2 over, it looks like what we want. And then basically what's happened, we've moved them all up 2, haven't we? Move them all up 2, so it now go between minus 1 and 5. So we need to draw asymptotes at, oh no, asymptotes at 5, that's at 6. Oh, nuisance. Oops, that's the wrong thing. Oops, where's my pen gone now? Lost it. Move that off. Start again. So if we put the asymptotes on at 5, a nice steady hand, and at minus 1. Ooh, good. Oops, it's going again. We're popular today. Sorry about that again. That was the dentist this time. Dentist tomorrow again. Oh, it's awful. Anyway. Right. So the range we were saying is between minus 5 and minus 1. So we'll write that as f of x, don't we, eventually? F of x is between 5 and minus 1. It's been up 2, isn't it? So it's gone. Centre of the shape should be there at 2. And you'd have it going down here and going down there, never touching. That's awful. Anyway, show your sketch looks better than mine. Right. Right, we've got some more range and domain. f of x is 1 minus cosh minus 1 of cosh minus 1 of x over 3. So here on the right is y equals cosh minus 1 of x. All right, we've got a few things going on here. The cosh has become a minus. We've got a translate in the y and a stretch in the x. So let me deal with the reflection first, I think I'd like to do. So if we started with y equals cosh, it's 1 of x. Let's say we want to reflect. I'd have to reflect because we want the y to change. That'd be x. Reflect in x-axis. So then we replace y over minus 1 equals cosh, which ends up with y equals minus cosh. Then what we do, change colour pen, we would, doesn't really matter if we want to do the stretch, let's do a stretch. Stretch by scale factor 3 in x, that would leave us with y equals minus cosh to the minus 1 of x over 3. That's easy. Then if we then do now translate, what would it be? It'd be 0 minus 1. That would give me, replace that with y plus 1. Alright, so it doesn't want to be that, does it? Might move. I want it to be my minus 1, so it's a plus 1 there. Oops, my fault. So replace y with y minus 1. That would give me minus cosh minus 1 of x over 3. And then we'll get the last one, y equals 1. We take minus 1 over minus cosh. Bingo. Right. So a lot been going on there. So let's think those things through with the graph here. So what the first one we were going to do, I'll get my highlighter. Look at that, highlighter. Reflecting the x-axis, then we're going to stretch, and then we're going to translate. So if I do these steps and then I rub them out, or we'll see how we go. So first one, if I was reflecting, don't draw this until the end. So reflecting that in the x-axis, we'd have that graph, won't we? Ooh, bad one. If I then stretched it by scale factor 3 in the x, so any x value would be times by 3. So 1 would become 1 times 3 is 3. Like this point here would become times 3, so it'd be 12. So it's getting a bit thinner really, isn't it? That's really bad. But it's small. And then what do? We go and move it up 1 in the y. So it would start there and go. So I can rub those others off now. That's not a nice graph, to be fair. But you can get the gist for writing range and domain. So the range, what can x be? Well, x can only be 3 or bigger. And the domain, oh, that was the domain, not the range. Who said that? Rubbish. It's me worrying about the dentist tomorrow. Cruel place it is. Right, the range is the y values, isn't it? So that's going from 1, and it would go down. It'd be a long time before it got right down to down to about 50, but it's still going to get there, minus 50. So it goes anything less than or equal to 1. Now we're done. And we'll state the largest possible domain of f of x. So I've done that. And for the domain in part A, find the range. Oh, I just think find the range in domain. What a silly worded question. Right, next. Oh, exercise 8A for you. Oh, good. Means I can have a rest. Or maybe not. Because we've got a bit to do, haven't we? We might want to whiz through these first before we get 8A. Come back to it in a bit. Because you're going to have 8A and 8B. So let's whiz on. Right, reciprocal functions. That's 1 over, isn't it? So when you're done, 1 over, back in normal maths, you did 1 over cos, 1 over sine, and 1 over tan. Remember what those came? They were sec, cosec, and cot, weren't they? Now we just put in h's on the end of those and get in sec, cosec, and coth. And we do 1 over the reciprocals, a bit like trig. It tells me how to pronounce it there, sec or sec. Cosec. I say that one anyway. And that one, coth. Write the above hyperbolic functions in their exponential form. Right. Well, we know that that is 1 over cosh. We know what cosh is. Cosh is a half of e to the x plus e to the minus x. So just 1 over that. So the half, the 2 pops to the top. You get e to the x plus e to the minus x. That, and cosec is 1 over, remember the third letter gives it away always, shine. So that's going to be 2 over e to the x minus e to the minus x. And coth, well that's shine, no, I can't say these things, can I? It's usually sine over, it's 1 over, I'll write that down, 1 over tanh. So rather than shine over cosh, it's cosh over shine, cosec. It's usually shine over cosh. So yes, it's cosh over sine, isn't it? Cosh over shine. So writing that one down, cosh, that would be that one. Oh, it's that one in here, let's write that one. That's cosh divided by shine, which is e to the x minus e to the minus x. Making a middle of this one. So you're doing fractions, you'd flip and change it to times. Let's just put a line down here. So I flip and turn it to times. So I've got e to the x plus e to the minus x over 2 times 2 e to the x minus e to the minus x. 2's cancel, and you're left with e to the x plus e to the minus x over e to the x minus e to the minus x. You've probably seen that quicker. And I've just written it, but never mind. Okay, and what do you think the exponential form of cosh 2x might be? That's cosh x, cosh 2x. So what we do to that one, answer would be, let's hope you've got it. Here it comes, revealed. Yes, shouldn't be a big surprise. Okay. Sketches. You can put them in your calculators and sketch them if you like. There's kosh becomes shek. Basically to get them 1 over it, remember, so 1 over 1 is 1, so we know it's going to go through 1. 1 over, like, say that's 1 over 4 becomes a quarter. That's why it's dipping down here, and so on. That's what it looks like that. When you do the koshek, well, shine is this. You do 1 over 0, infinity. That's why it's got an asymptote there. Then you come out here, 1 over 1 is 1. And then 1 over 2 is a half. It goes down, 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 etc. And similar on this sort of thing here. On these other numbers here, when you got here, 1 over a half is 2, so it goes up that way. So it makes that sort of hyperbolic type thing. Right, range and domains on them then. Let's squeeze these in. So that's that. So the range here, what's the y values between? Well, our f of x is between, it can equal 1, but it doesn't equal, oh, it doesn't equal, it doesn't equal 0. And this is an even function, isn't it? And the domain, that's the x values, they can go on forever, so x can belong to the real. This one, this is an odd function, and we call this one's also an odd function, isn't it? And the range and domain of this one is, I've written them, but I'm in the way. I'm going to have to write them here, and then you probably can see them when I've moved me, but I can't see them at the moment. So range, I'm twittering on about range domain for this graph. The range, the y values, y can be anything, can it? Or can it not? It can't, can it? There's something it can't be. It can't be 0. So it can be anything but 0. So we can write that in various ways. We can put you could put f of x is greater than 0 and f of x is less than 0. Or you could just put f of x belongs to the reals, I think, except f of x cannot equal 0.
According to Wikipedia, FX is an American pay television channel owned by the Walt Disney Television unit of the Walt Disney Company through FX Networks, LLC. It is based at the Fox Studios lot in Century City, California. FX originally launched on June 1, 1994.
No, we got it. Amazon, shut up. Alexa, be quiet. Sorry about that. I didn't expect Alexa to pop up with f of x. We might have learnt something now, if you heard that. Right, domain. That was an interesting interruption. Domain, what can the x values be? Well, it's a bit similar, isn't it? The x values can't be 0, so f of the x values belong to the real, except x cannot equal 0 either. Wonderful. Oh, there's another one. Coth x relates to tangent. It's 1 over tanh. Tanh is an odd function. What's coth going to be? Right, well, there's asymptotes here at 1, 1. So that means all those, the heights of all those green bits, all their y values are between 1 and -1. Now, what do we know when we put 1 over a half, or 1 over a third, or 1 over a fourth, quarter, 1 over a tenth, 1 over any fraction, it's going to be bigger than 1. Yes, 1 over a half is 2, 1 over a third is 3. So we're going to have nothing, right? Nothing, no values less than 1. And no values between 1 and minus 1, basically. Let's say 1 over, because it's reciprocal, 1 over minus half would be 2. 1 over 9 tenths would be 10 ninths. So it's getting smaller that way, but bigger that way, isn't it? So you'll end up with this sort of graph. Because you can't have 1 over 0, can you? So it doesn't exist here. So there's another like asymptote down the middle there. Asymptote at the x-axis, the y-axis, which we call x is 0. You've got those two bits of graphs. Domain for those, well, the range is what's the y value, so y can be anything. Y, so I'll call it f of x, not y. F of x can be less than minus 1, or f of x can be greater than 1. The domain, well, the domain can be anything, the x values can be anything except for 0. So x can belong to the reals, but x cannot equal 0. Do. And this one is also a odd function. Right, range and domain of inverse reciprocals. Wow, so now we've got the inverse of the check. So inverse of the inverse of the reciprocal. Show it's this log function and state the domain of it. If we consider first of all check, that's the graph of check. Now, if we're going to have an inverse of it, inverses must be 1 to 1. But clearly this isn't a 1 to 1 because we've got two values of x here giving the same value of y. So that's not 1 to 1. So we have to sort of ignore part of the graph in order for this to work. So we're going to take x to be greater than 0 and just find, that's why it was check. Just find the inverse for that part. So we've got here, a bit similar to what you've done in AS maths with, you must have done it with Shine and Kosh inverses. Here you've got y equals check to the minus 1 of x. Well, it has both sides by check. So you get check y equals x. Now check, you've done check x before, so we're just going to put a y where we see the x. A couple of slides ago we said what that was because that's 1 over a third letter. So it's not a half e to the y plus e to the minus y, it's the upside down of that, so it's 2 over e to the y plus e to the minus y, and that equals x. So we might multiply through, so we've got 2 equals x, and then those. Take the x back down there, get rid of that x. What we're going to do next is we're going to times through by, let's times through by e to the y. So we get 2 over x e to the y equals e to the y times e to the y, gives you e to the 2y if you like, plus e to the y, e to the y, that just becomes 1, doesn't it? Well, I'll write it down because then you'll see what's going on. E to the minus y times e to the y. Add those together, e to the 0, which would be 1. So that's 1. Can we write that? Let's write the 0. This is very quadratic. 0 equals e to the 2y minus 2 over x e to the y plus 1. So it's one of those hidden quadratics. Right, hidden quadratics. Because that's e to the, I hope you all know that's e to the y times e to the y. So what we'll get, hidden quadratic. Oh, Sean's in the way. Oh, lots of, oh, we've got space on the next slide, I think, so I don't have to whip this over to the next slide. I think I will. No, I won't. I'll do it first. I'll do it here first. So e to the y, now quadratic formula, equals minus b, that's 2 over x, plus or minus square root b squared 4 over x squared b squared minus 4ac 1 times 4. Right, over 2a over 2a 2 right, sort that out is basically what we do. So I'm going to write that as, before I whip over, e to the y equals 2 over x plus minus square root, I'm going to put these over a common denominator of x squared. So we'd have 4 minus 4x squared, wouldn't we? All of that over 2. Now we jump to the next slide. The only difference is I'm going to pull out here a 4 and pull out the x squared. Right, so we'll do that. Right, so say I'm going to write e to the y equals, what we've got here, we've got 2 over x plus minus square root. The only thing we'll do is pull out the 4 and pull out the x squared. So what you've got there now is just 1 minus x squared, isn't it? And all that's just over 2. So I pull that out, we've got e to the y equals 2 over x plus minus square root that 2 over x, and instead square root of 1 minus x squared all over 2 times each term by, we're timesing by x over x basically, times by x over x, times the top by x, the bottom by x, you're only timesing by 1, aren't you? So that would give me 2 plus minus 2 root 1 minus x squared all over 2x. Then hopefully you can see the 2's will cancel. That 1, 1, 1. So we end up with e to the y will equal 1 plus minus square root of 1 minus x squared over x, and when you log that you can get rid of the e, can't we? So we can say y will equal ln 1 plus minus root 1 minus x squared over x. However, ignore, here, we ignore the negative option. Why? Well, to ensure that e to the y is positive. So up here you couldn't really have the minus, so that's basically, let's put a big star there. e to the y can never be, e to anything can never be minus, can never give you a negative number. So to ensure that, we should get rid of the minus there. So that should be gone there. Doesn't exist. So what we have got then is that y equals ln (1 minus x squared over x squared). Kind of missed out. Oh no, it's not x squared. What is for x squared? Just x. Right. We've got to state the range and domain, haven't we? And this is, that is, y is, sorry, should have written y is, right at the beginning, y, we're given y equals shec to the minus 1 of x. So that means that shec, so minus 1 of x will equal ln 1 plus root 1 minus x squared over x shown. But in the domain and the range now, we can see from that, well, to make that, you can't square root a negative, so x squared has to be less than or equal to 1, doesn't it? Can't be anything bigger than 1, or you'll be square rooting a negative and that wouldn't be happening. What else about the domain? Well, if you remember from the beginning, we said we were instructing that x must be greater than 0, didn't we, in the very first part? We weren't considering the other half of the graph because that would make it have an inverse, wouldn't have an inverse. So we said x had to be greater than 0. So if we've got to satisfy both of those, this means, oh, x can be plus or minus 1, couldn't it? Doesn't really matter. So if we're satisfying both of those, we're saying basically that x will end up being less than or equal to 1 or greater than 0. So that is the domain. We wanted the domain, didn't want the range, thank you. Right. So hopefully we get that thing. If I just make a quick note there in case you were lost, we said that thing there have an inverse. Must have. Oh well, you know what I mean, from beginning. A bit arrow typed in the black. Right, and put there satisfies both. Okay, have I finished? Hope so. Yes, I've finished. So it's exercise 8B as well as 8A. If we've got time now, go and grab the textbooks and have a little bit of fun yourself with a few questions. You'll find they're on the homework too. I'll see if there's too many in the exercise to limit them on the homework, but maybe there's not. Have fun. Bye bye. Enjoy the weekend of maths.